In the previous video, we have done up to here. So now we will start from F and G. Part F, so let me copy what we have done in the previous video. The second derivative was very complicated. X transpose and second derivative h and y over f minus 1 minus y over 1 minus f, and then minus gi squared times yi over fi squared plus 1 minus y and 1 minus f squared. All right, so this is the second derivative of the loss function, and then we are going to bound it. So first, like the assumptions we have is h is bounded, so let's say c of h, and we have bound for g is also bounded, and y is easily bounded because y is 0 or 1, so y is always greater than 0 and less than 1. So that means 1 minus y is also less than 1 and greater than 0. So they are usually okay. But the problem is in the denominator, right? 1 over f. How can we bound it? To bound it, like we are going to use the lower bound for f. If f is greater than delta, that means 1 over f is smaller than 1 over delta. Similarly, if f is less than 1 minus delta, then this inequality means 1 minus f is greater than delta. That means 1 over f is less than 1 over delta. So in this way, we are binding a lot of things. So whole part of these guys will be bounded. That is, say, let me turn the page. So supremum about beta for the norm of this is bounded by, first I will just keep x as it is. We are just taking supremum over beta, and so beta is included in h, f, g, right? Actually they are functions of beta, so we are going to bound, say, h, and this part y over f plus 1 minus y over 1 minus f, plus actually every minus sign turns positive, plus because it's all absolute values, gi squared times y over f squared plus 1 minus y over 1 minus f squared. All right, so this is bounded by c1, this is bounded by 1, this is bounded by 1 over delta, 1 over delta, so 1 over delta plus 1 over delta, and plus this is bounded ch, this is bounded by cg squared, and this is bounded by 1 over delta squared, plus this is also 1 over delta squared. Okay, so beta enters only this part, right? H, f, and g, right? So in the end, this is also just a constant that does not depend on beta, and so now, so expectation of supremum beta of the second derivative is less than expectation of, say, I will write these guys as just one constant. Say, then a constant times xi transpose norm. So this is finite if expectation xi transpose norm is finite, which is actually implied by this assumption. By the way, I forgot to mention here, so I had to include G here. I will update the problem set accordingly. Anyhow, so we can bound like this, right? So it's very simple, but just very annoying. Next, we are going to determine this guy. So first, remember the first derivative equals x times gi beta 0 times yi over beta fi minus 1 minus yi over 1 minus fi. This was the first order derivative, right? Of course, here fi should be beta 0, fi beta 0. And we are calculating expected value of its variance. Okay, so we are going to calculate this. Then you can write this as, by the way, this is k by 1 dimension, but this is 1 by 1 real number. This is also 1 by 1. So dimension is pretty simple. It is xi transpose times gi beta 0 squared times all of these guys, yi over fi minus 1 minus y over 1 minus fi squared. That is how we calculate this, right? So to do that, let me calculate. We are going to use law of iterated expectations, and then we need to calculate this first, yi over fi minus yi over 1 minus fi squared. So we have to calculate this first. That is, we just have to rewrite. Let me rewrite. Excuse me. So what I had to say here is conditional on xi, right? This is what we have to calculate inside the law of iterated expectations. That is expectation yi squared fi squared and plus 1 minus y squared and 1 minus f squared times 2 times yi 1 minus I times fi 1 minus f given xi. Right? So here it looks complicated but actually pretty simple. First, let's look at this. If y is 0, then this is 0. But if y is 1, this is 0. So either case, this multiplication is always 0, right? So we can ignore the third term. And think about this. So, and now this guy, yi squared is like, if yi is 1, its square is 1. If yi is 0, square is 0. So yi squared is simply yi, right? Square does not do anything. For the same reason, you can see that 1 minus yi squared is 1 minus y, right? So it is simplified. So that means, and in denominator are non-random once conditional on x. So we will rewrite this way: yi given xi divided by fi squared, okay, plus expectation 1 minus y given xi over 1 minus fi squared, right? And the third term goes away, okay? So this much comes to here, and this much comes to here, and third term vanishes. And then, you know, this is f, and this is 1 minus f. So 1 cancels out, each cancels out. So we get this, and that is f times 1 minus f in the denominator. Okay? So then, finally, it goes to expectation xi transpose gi beta 0 squared times 1 over fi beta 0 times 1 minus fi beta 0. This is what you get, right? And this is pretty similar to what we obtained in the previous let me see, I lost our result, right? So in the previous video, we calculated the second derivative expectation as expectation of xi transpose gi, exactly the same thing, squared beta 0, 1 over fi beta 0, and 1 minus fi beta 0. So it was the same thing, right? So we are happy to cancel out later. By the way, this equality is proved by Fisher, the inventor of maximum likelihood. This is always true for maximum likelihood estimator, right? Expectation of this guy equals minus expectation of sorry, right, like this. So there was minus sign here. I'm sorry about that. So the second order derivative expectation of log likelihood function equals the variance of the first order derivative. So in the maximum likelihood estimator literature, we call this score function. And this is Fisher information, and these guys are called Fisher information. Later, its inverse becomes the variance of the maximum likelihood estimator, right? So this is just a special case of the maximum likelihood for binary variable. So we have done this one. And now let's derive the limiting distribution for beta hat. Okay, so you just need to check the sufficient conditions first. Beta 0 should be unique maximum, and we can show that very easily. And second, we have to show that B is compact. So we assumed it. And 3, the log likelihood function is twice continuously differentiable. That's also trivial. And 4, the Hessian matrix this is H0 is non-singular. We proved it. And also I changed the numbers. We need to dominate the second order derivative. Second order derivative should be reasonably bounded. And finally, this omega exists, right? Then under these assumptions, under these sufficient assumptions, then we can show that by the lemma converges to normal distribution with V, where V equals H0 inverse omega H0 inverse. But in our specific case, as I said earlier, H0 is minus omega, right? Yeah, right. So they'll be canceled out, and it equals omega inverse, or that is H inverse, right? Okay. Let me see. Something is, so this is so omega inverse is quite like right. So H inverse is wrong because H is negative definite, right? I'm sorry about that. So anyhow, that is the variance. Okay, so that means the variance equals expectation xi transpose gi squared beta 0 1 over fi beta 0 times 1 minus fi beta 0. That was the variance. Its inverse, omega is this, so the variance is its inverse, right? Then the last question is, how can we calculate the variance? The variance of beta hat n is approximately v over n, right? Because the convergence rate is square root n, right? And standard error of this estimator is square root of this guy, right? Now let's think about estimating this v. Let's think about the problems. First, we do not know beta 0. Beta zeros are here, here, here. So we are going to plug in beta n hat. Okay, and also we are going to replace expectation with 1 over n and summation. Okay, so that means to calculate the variance, so estimate beta hat first, and then compute like gi hat, which is gxi beta n hat, and also calculate f hat, which is f xi beta n hat. So we can calculate f and g. F is known function, and g is just known function's derivative. So like we can calculate them if beta is available, right? And then the variance hat is 1 over n. So, and inside xi transpose, we can calculate x, we observe x directly, and gi hat squared, and 1 over fi hat times 1 minus fi hat. You can calculate this for every I, and then take the average, and then take their inverse. So this is how you calculate the variance. Then standard error will be straightforward.